And welcome back. As we wrap up our cosmic journey through our solar system, the last thing we kind of really need to explore is that of meteorites themselves, also referred to as sometimes as stones from heaven. So, we of course talked about meteors, but what about meteorites? What about those chunks that actually break through the atmosphere? Well, recall that any fragment of interplanetary debris that survives its fiery plunge through Earth's atmosphere is referred to as a meteorite. Now, meteorites fall only very rarely in any one locality, but over the entire Earth, thousands of fall each year. Now, some meteorites are loners, but many are fragments from the breakup in the atmosphere of a single larger object. Now, these rocks from the sky carry a remarkable record of the formation and early history of the solar system. And the first thing to understand with meteorites is that of a meteorite falls, because meteorites are found in two ways. First, sometimes bright meteors or fireballs are observed to penetrate the atmosphere to low altitudes. If we search the area beneath the point where the fireball burned out, we may find one or more remnants that actually reach the ground. These observed meteorite falls, in other words, may lead to the recovery of fallen meteorites, which we can then use for things such as study and analysis. There are, however, many false alarms about meteorite falls. Most observers of a bright fireball conclude that part of it hit the ground, but that is rarely the case. The meteorite itself is also ice cold in space, and most of its interior remains cold even after its brief fiery plunge through the atmosphere. A freshly fallen meteorite is more likely to acquire a coating of frost than to necessarily start a fire. Now, the other way we can kind of really get a handle on meteorites is to have a meteorite find. And this is typically done by discovering unusual looking rocks that actually turn out to be meteoric. We call these rocks that we find meteorite finds because while we couldn't observe the fall of it, but we could find it in the earth. Now note that the public has become much more meteorite conscious, and many unusual fragments, not of all which turn out to be from space, are sent to experts each year. Now outside of Antarctica, genuine meteorites turn up at an average rate of 25 or so per year. In Antarctica, it's obviously much higher because with the snow covering, it makes it pretty easy to find rocks that kind of stick out. Now, most of these rocks that we find end up in natural history museums or specialized meteorological laboratories throughout the world, although there is a growing group of private collectors that's interested in them as well. And with that being said, are all meteorites the same? Because, of course, we talked about how they come from comets and occasionally other things, good breakup of cosmic dust. So, do we have a classification system for meteorites? And the answer is yes. Yes, we do. The meteorites in our collections have a wide range of compositions and histories, but traditionally have been placed into three broad classes. First are the irons, composed of purely metallic nickel iron. Second are the stones, a term used for any silicate or rocky meteorite. And the third are the rare stony irons, made from, as the name implies, a mixture of stone and metallic iron. Of these three types, the irons and stony irons are the most extraterrestrial because of their metallic content. Pure iron, for example, almost never occurs naturally on Earth and is generally found here as an oxide or other mineral ore. Therefore, if we ever come across a chunk of metallic iron, it is sure either to be man-made or from a meteorite. And again, if we look at these meteorite types and get some good visual representations here, if we look at piece A here, this piece of the alanated carbonaceous meteorite has white inclusions that may date back to well before the formation of the solar nebula. In image B, we have a fragment from the iron meteorite responsible for the formation of the meteor crater in Arizona. And in image C, this piece of the ilmenite stony iron meteorite is a beautiful mixture of green olivine crystals and metallic iron. And so now, looking at these, we can start already saying, well, is there a way to start looking at the ages and the compositions of the meteorites? Because remember, we said it's very difficult to look at meteors, but what about the ones that we have actually been able to find? Well, meteorites include the oldest and most primitive materials available for direct study in the laboratory. The ages of stony meteorites can be determined from the careful measurement of radioactive isotopes and their decay products. Almost all meteorites have radioactive ages between 4.5 and 4.56 billion years, which is as old as any ages we have measured within our own solar system. The traditional classification of meteorites into irons, stones, and stony irons is easy use because it's obvious from inspection which category a meteorite falls into. More scientifically significant, however, is the distinction between that of primitive and differentiated meteorites. The differentiated meteorites are fragments of larger parent bodies that were molten before they broke up, allowing the denser materials to sink to the centers. And we've seen this kind of thing before when we started talking about, for example, metallic asteroids. Like many rocks on Earth, they have been subject to a degree of chemical reshuffling, with the different materials sorted according to density. Now, differentiated meteorites include irons, which come from the metal cores of their parent bodies, stone irons, which probably originated in regions between a metal core and a stony mantle, and some stones which are composed of a mantle or crust material from their differentiated parent bodies. Now, if we look at the most primitive meteorites, we might see something a little different. For information on the earliest history of our solar system, we look at the primitive meteorites because we can look at the spectrum of sunlight reflected from asteroids and compare their composition with those of primitive meteorites. Such analysis indicates that their parent bodies are all almost certainly asteroids, which is a great insight to, again, looking at our own solar system. When we talked about, for example, the different types of asteroids and how those give us a window into certain things. Same thing with comets. Now, since asteroids are believed to be fragments left over from the formation process of our solar system, it makes sense that they should be the parent bodies of these primitive meteorites. Now, the great majority of meteorites that reach Earth are primitive stones. Many of them are composed of light-colored gray silicates with some metallic grains that are mixed in, but there's also an important group of darker stones called carbonaceous meteorites. Now, these meteorites naturally contain carbon, but we also find various complex organic molecules in them, chemicals based on carbon, which on Earth are the chemical building blocks of life. In addition, some of them contain chemically bound water, and many are depleted in metallic iron. Now, this gives us an interesting window because it suggests that meteors could have actually helped provide some of the molecular building blocks of life very early on in our planet's history.